Good morning, everyone. Welcome to the Online Help Center for Small Water Systems 2022 webinar series. This is our last webinar for 2022, and I'm very excited to have one of our funding partners present to us, Indigenous Services Canada. My name is Satwinder Paul. I'm a teaching professor and program coordinator for the Water and Wastewater Technology Program and co-creator for the Online Help Center for Small Water Systems in BC. Before we begin, I'd like to do the land acknowledgement. I would like to recognize that Thompson River University campuses are on the traditional land of the Tk'emlúps, Secwépemc, and the Txela campuses within Secwépemc Ulu, the traditional and unceded territory of the people of the Secwépemc. Thompson River University, with their partner, hosts an annual webinar series and courses dedicated to providing relevant technical information, resources, and tools to small water system owners and operators and First Nation small water systems on issues of treatment, regulations, operation, maintenance, and water quality monitoring. At the same time, we hope to also provide a forum for systems to share information with one another. The Online Help Center strives to assist all small water systems in BC to implement a multi-barrier approach to drinking water in order for systems to consistently provide safe, potable drinking water to their communities in compliance with government regulations. These webinars are scheduled for every 2 months in 2022, and then we have our 2023 schedule on the website, so please have a look and please register for 2023. We have a great show of presentations coming to you. All the webinars are approved for EOCP CEUs, and they're allotted 0.1 CEUs per webinar. You must attend the webinar online in order to receive those CEUs. So we will begin by 1 hour presentation first, and then follow up with a half-an-hour question period. During the duration of the presentations, if any question arise, please jot them down in the question section. We will do our best to address those questions after the presentations. Now I'd like to introduce our presenter. So we will be having this presentation is on treatment methods to meet the new health maximum allowable concentration for manganese. These MACs were set in 2019. After introducing why the MAC was established and who it affects, we will also discuss various treatment and processes for addressing manganese removal, provide advice and insight from health authorities, suppliers, and operators on how to address these MACs, and understanding of how small water system can derive and implement their own solutions to meet these new health and aesthetic standards for manganese. Our presenter is Ted Molyneux. He graduated from the University of British Columbia Civil Engineering program in 1983, then worked for 2 decades with Langley, BC Groundwater Resource Development and Water Treatment and Distribution Sales Services and Contracting Companies. In 2003, Ted became a senior water engineer with Indigenous Services Canada. There he works with British Columbia 200 First Nation communities, supporting their 270 community water systems in supplying safe water. For over 5 years, Ted has been striving to incorporate reconciliation into his work and life. So we are very pleased to have Ted do this presentation. And as I mentioned, Indigenous Services Canada is one of our funding partners for the Online Help Center, and we are very grateful to have this last webinars from them. So Ted, please take it away.
Thank you, Satwinder. And it's nice to be here today. I'm coming to you from North Burnaby on the territories of the Musqueam, Squamish, and Tsleil-Waututh people. I grew up in Naramata, changing sprinklers as a child. Well, maybe not as a child, but as a teenager anyway. And then during most of my career, or the early half of my career, I worked selling and installing pumps and along the way water treatment equipment as well. And a lot of the people that I dealt with, a lot of our clients were small water systems. So I've been working with small water systems for a long time. Then I got involved with BCWWA Small Water Systems Committee. So small systems are been the focus of most of my career, actually, although I have worked with the largest municipalities as well. I have to apologize because I'm using somebody else's presentation. So it had some animation in it that I didn't realize was there until we started going live here. So if there's any glitches, my apologies. And I think I'll stop showing my video now. That way I'm not looking at myself and I can just focus on the topic at hand. Oops, muted myself instead of getting rid of the video. Okay, so this presentation was put together by Dave Tamlin, Public Health Engineer at the First Nations Health Authority. He was with Northern Health Authority. He was their Public Health Engineer there in Prince George. Kimberly Brown is their new Public Health Engineer, and she took Dave's presentation and started modifying it for our purposes here. We got some input from Grant Robertson. He's a certified water technician from Water Quality Association. He's with Home Plus in Kamloops. I want to thank Sant Winder for inviting us to do this. And finally, Sanjana Akela, who is a very new colleague to me, but I had worked with her before when she was with that Golder WSP, and she's a water treatment engineer. Both Kimberly and Sanjana were instrumental in putting this together. So what's the issue with manganese in drinking water? Well, there's definitely aesthetic concerns, and that's what we've mostly worked with for a long time. Although the manganese itself is tasteless and odorless, we often have tastes or odors associated, but it's not the manganese. Often we've got a black and brown staining, some turbidity. Right now, the aesthetic objective is down to 20 micrograms per liter from 50. But for a long time, many of us in the industry knew that 50 was kind of a hit or miss number. Sometimes we had problems lower than that and sometimes above it. Why? It all gets down to water chemistry. We're going to talk about that. But at the end of the day, when people see water like this, they're not very confident in it. And it's really weird because the big problem is clear water because it could have bugs in it. Whereas when it's like this, I'm thinking it's groundwater, there probably isn't any bugs. So it's kind of backwards, but that's the way water is. So what are the health concerns? It is an essential element, and having it as a deficiency is unusual. The manganism is what causes an issue when the levels are getting higher, and that's been known for a very long time, but it really wasn't driving this. It was pretty uncommon to see these elevated levels and these issues, because the water, by the time it gets to that point, it's pretty bad for the most part. I won't say in every situation, but for the most part. Now we have an epidemiological association with neurological effects in children. And this has led to a new MAC, 120 milligrams per liter. So just to keep this in perspective, our aesthetic goal before was 50. And when they came up with this MAC in 2019, the aesthetic dropped down to 20, and now we have the MAC at 120. And this is, you can see that the target audience for this is bottle-fed infants and very young children. So getting back to what the risk is for people who aren't infants, you look to the guidelines for Canadian drinking water quality, and they talk a lot about the risk. All of the regulators do that. They look at risks, they look at studies, and you can see that the number here is over 300 is when we start having issues. And realistically, by the time you're getting to 300, generally speaking, your water is going to be pretty bad. We're probably not really going to want to be drinking it, but like I say, that's a generalization. But so what was the new thing? And it's this study of school-aged children that was done in Quebec over a decade ago. And when this came out, there was a lot of controversy and a lot of dialogue about how true this information, how correct it was, what the real risks were. So here we are with IQ in children and tap water concentrations. They do this nice little line through here, so they're doing their statistical analysis. And then we get to this statistically significant difference at 120. And that's how they set these things. There were other jurisdictions in North America who took interest in this immediately and did act on it. At Indigenous Services, we did look at this, and we found very few of our community water supplies actually had elevated levels of manganese. Oh, and the other thing to important note is we're talking about groundwater here. And I find it interesting, it's page 6 before we actually mention groundwater. This is primarily a groundwater issue. Why? Because in groundwater, we get metals coming out often that are dissolved in that water. And we're going to talk a lot more about that. And this was became a news item, and that's when it really started to become important. Well, it was important before, but when it gets in the media, there's accelerated efforts to address these concerns. The other thing that is of interest, though, is trying to convey the real risks. People tend to see these numbers like a 120 as some kind of a light switch, whereas at 100 you're alive and at 140 you're dead, and it's nothing like that at all. You can see from the slope that it's not an on-off thing, it's a sliding scale thing. And one thing I want to say too, it doesn't mean that these children are all of a sudden completely, you know, that they're. I'm lost for words here. I don't want to say the wrong thing, but it's a smaller change that needs statistics to find it. So you're not going to go to these communities and go, wow, why are all these people not the brightest in the world? It's not like that. But it is something that is important to people who are purveying water, that we take appropriate actions. Just a little bit of chemistry here. There's manganese right beside iron. Iron and manganese, those are the veins of groundwater in much of this province, not elsewhere in Canada. Mostly if we've got some rocks nearby in your hydrogeologic setting. And then what we're always worried about here is the oxidation state of the metal. So this is a nice little table, and Mn2+ is clear. And as we take electrons away, you go to 3, the dark brown, lower solubility, and then 4, which is the black, and then you end up at 7, which is soluble in pink. But mostly what we're seeing is the 2, 3s, and 4s. And oxidizing is stripping away an electron. And so an oxidant knocks you from 2 to 3 to 4 to 7. In iron, it's 2 and 3. And when we talk about solubility and insolubility, really what we're saying is that that clear stuff that's soluble, it's staying dissolved in the water, so you don't see it. You start to see it when it becomes insoluble and turns into a particle. So that's very important, this concept of being soluble going insoluble. How you deal with those two are different. Okay, and I'm not presuming you're going to remember any of these things. This is the technical thing. The more important stuff is what we're going to do later on with our system, how we're going to deal with it. But essentially what you're seeing here is that pH is very important. You look at that 7.5 line, and boom, all of a sudden you can make it dissolved into a solid. So if you are going to remove, you want to stay in that blue area, but if you want to get into a solid, you go into the gray area, and that gray area is higher pH. So usually that's what we're trying to do, is get to the higher pH and ORP. Now you can see that in the ion exchange RO galls, which is reverse osmosis, which is a membrane treatment system, we're wanting to keep it low and the ORP low so that it stays dissolved, because if it turns into a solid, it's going to mess up our membrane. And this ORP is oxidation reduction potential. You don't hear people talking about it a lot. It's related to dissolved oxygen, and with groundwater, oftentimes we start getting lower numbers as the oxygen has been consumed out in the aquifer. Another thing is whether or not they're small particles or large, and we'll talk again a little bit more about that. But for this group, probably the more important thing is for filtration, we want to make it solid. And we'll often use chlorination to sort of help in that process. Level of service standards, if there's First Nations communities, you would know what it is, or people that work with, and I'll say First Nations because in British Columbia, we have First Nations communities. They're RMAT, but they are not living on the reserves in BC. Well, they might be if they're part of a particular community. So we have just over 200 First Nations in British Columbia. We have 270 water systems, and for us, we consider an individual system to be less than 5 connections, and that's an Indigenous services rule. And you're seeing Dave put here that equates to no money. We don't have funding at this point in time for individual water systems, although in a recent court case that was won or settled, part of that court case was how can the department help individual water systems? And that's a very interesting concept because that's very foreign in the world of water supply, that you would help individuals. And now our department's been asked, we're the first probably to try and tackle that, and it is not going to be easy. Our community water systems were 5 connections and over. British Columbia, a system is 2 connections and more. And we're an oddball in British Columbia. There is some limitations on that now, like your 2 homes sharing a well in your family. But it's very kind of an odd thing. And now with Indigenous services, we'll provide funding. So here you see this split between the dissolved and the solids and what we do with them. And for our community water systems, we'll often be over on this side, but for these treatment processes, starting to the left, we have ion exchange. We'll talk more about that. Biological oxidation is not very common here. It's almost rare. There is this quote unquote green sand, but most of that falls in the umbrella of filtration, oxidation filtration systems. Green sand was an old school type of media, but that's the terminology that has stuck around over the decades, even though there's a lot of change in what we're using now. You get into the direct oxidation and precipitation, and then these separation processes where you'll have clarification and filtration, and you might use media, or you might use MF or UF, which again are membranes. So MF is microfiltrations and UF is ultrafiltration. We're not going to talk very much about membranes because in community water systems for small systems, they're not a typical solution. And in the membrane world, I've mentioned reverse osmosis. That is what we'd call the tightest. And then there's nanofiltration followed by ultra and membrane. The first two are high pressure, the second two are low. There's differences in how they are operating, set up, and the energy that they take, etc. We're going to talk about RO, but it's more of a, if you're going to do this as an individual solution in your system, how an individual might take care of it within your system, but not you as a utility purveyor. Some small systems might get to microfiltration. RO is you want to stay away from that as much as you can, and that's used where we have certain poor quality waters, but the complexity is very high. So realistically, it's this green sand that is the one that is probably going to be the thing that you're going to talk most about. And again, I don't want to, it's in quotations, it's oxidation filtration process. And he's mentioned sorption and catalytic oxidation. Again, we're getting way too into the weeds when we start getting into all of these real fine details. You have to take courses to be able to understand these types of things. Ion exchange is conceivable for small water systems, actually, although it's noted here something for an individual water system. It is conceivable that it can be used on a larger scale, depending on the water quality. All of this comes back to what is your water quality. Okay. So for the independent water systems, we're really, if it's dissolved, so you couldn't see it and you weren't getting staining, you could use the NFRO process and or the ion exchange. And we'll show you some setups for that very shortly. And again, here it mentions MFUF, which is possible, but I'm thinking it could just as likely be an RO, but it depends on the person that you're talking to, who the vendor and supplier is. Because often if it's a particulate, we're going to try to filter it. So we'll talk about this one. So here's a typical setup, and some of you may have seen something like this. And here, Dave is mentioning POE is point of entry. But Dave made this presentation to EHOs who would have understood this. And I apologize that I didn't have time to go through, because when I look at this, I don't even think about it. POE, point of use, those kind of things. POU is point of use, POE is point of entry. So this is point of entry because the water is coming in from the water well on the right-hand side bottom, up and through the system and then into the home. A point of use, we'll look at that too, and that's usually under a sink. So here we've got this water coming in. Dave used one that that was for hardness. So it says hard water in, and then it goes around to this softener. We'll show more pictures of these softeners and media vessels. They look like these tall, skinny things with a little controller on top. And for the softening, they have that salt brine tank, and then the water's out to the hot water tank and beyond. Air gap for the backwash and the rinse setup. So if you're in a home and you could use a softener, this would be the setup. And if you had hardness, this is what you'd do. But like we say, within certain parameters, you can use it for iron and manganese. And how it works is the water normally comes in through that valve at the top. They all have these valves. This is the whole softening world. And if you're on the other side of the Rockies, you would have heard about softeners. And all our equipment comes from the prairies, because all of these, so many people have softeners out there because their water is hard. So it has calcium in it, and we're going to bump in here in this media. We're going to bump calcium, or the media has sodium on it that it got from the salt, and it's going to exchange, which is why they call it ion exchange. It's going to exchange the sodium for the hardness. So normally it comes down through the media and then up through that collection tube and out. During regeneration mode, it's going to take that number 4, which is the salt, and there's water in there, and it makes a brine, a salt brine, and we take and we feed it down and into the media, and then back up and out, and then there'll be a backwash cycle, and then a rinse cycle. These numbers didn't really, I thought this was maybe a Pentair diagram. I didn't think they did a very good job of putting the numbers with what they were talking about, and it gets worse. But anyway, the controller is this number 5. So that's an electrical mechanical thing, and it'll do this regeneration process after so much time, typically. With your community systems, though, it can also be done by the volume of water that's going through, and it can be done by a pressure drop. But the basic for home is time. So Dave's got some sizing information there. Your systems are bigger. These would be for smaller homes, and the flow rates can be even less than that. And this one has a carbon filtration setup in it as well. So there are times when you'll use carbon to help as a treatment step, pre or post. In this case, it's post. It's often the case. And this one also has this little 5-micron pre-filter. So pre-filters, which are using carbon, or pardon me, not carbon, but cartridges, are very, very common. And that's your standard household one that's in front. They can be longer and they can be bigger, and eventually they end up in a stainless steel vessel that can hold multiple cartridges. And that's not uncommon for a community system. And there's different types of cartridges. So this one's measuring 5 micron. That's the big thing, is how many microns. But in that filter world, that cartridge world, there is a whole ton of different cartridges. In all of this, there's a whole world of in any one of these things. So again, Dave was using Pentair. Pentair is one of the largest companies in the water supply world. They've grown and grown over the years. They were tiny, well, they weren't tiny, but they were very small when I started. Now they're huge. Now this is your point of use system, and it's using reverse osmosis. So reverse osmosis is the tightest membrane, and it's rejecting monovalent ions and anything bigger. But it was made to reject salt from salt water. So it doesn't allow the salt to go through the membrane. And what drives it is osmosis and osmotic pressure. So you pressurize one side, you force the clean water through to the other side of the membrane. We've taken out all the slides that show the different types of membranes, but you can Google it. You can find all the different types of membranes and how they're made. The important thing here is you see you've got these 3 cartridges at the bottom. That is very, very common. There's usually at least 2, sometimes 3. In this case, there's a 5th one behind. Sometimes there's 4 down below. There's a number of different configurations, but usually they've got something that tries to take out the bigger, lumpier stuff. And then there's GAC, granular activated carbon, and then even a carbon block on this one. And the activated carbons will take out lots of different things, as does the carbon block. And there is a little pressure tank afterwards that stores the treated water, because ROs, reverse osmosis membranes, don't produce very much water. And you see there's a drain line. They also waste water. So for every gallon you're producing, for these smaller systems, you could be wasting another gallon of water into the drain. So they store the water under pressure, and then when you are using it at the tap, you've got what's in that little pressure tank, and it's not a lot. It's like a gallon of water, or along that kind of line, like 4 liters, maybe 10, I don't know. But it's not very much. It's mostly for drinking and some cooking, which is going to be fine with manganese when you're trying to deal with it. Okay, Dave had having a TDS meter in here, $20 to $40. The cartridges last months, and the RO will usually last about 12 months, the membrane itself. Okay. So this is not an uncommon type of setup, and an actual real picture of what one looks like. Notice this WQA certification process. That's the Water Quality Association. And there's a lot of talk about trying to get them more involved in this process to help bridge a gap between yourselves and the vendors, some of whom will have a certification, as Grant did, and this equipment being Water Quality Association certified. And I think I forgot to mention this NSF, which is the National Sanitation Foundation. So this is an organization in the States. You pay them money and they make sure that your stuff is okay to be used in drinking water, and it meets a standard. So that is typical. They have all sorts of different, this one is 58 before, I think you saw 55, and others for the softeners. So it's a testing system. Here, look, you got another one. You got coconut. This one mentions a brand, Film Tech. That is an actual brand of membrane. There's others. Okay, 90 gallons per day. So that would be 360 liters per day. The average Canadian uses about 300 liters per day. So that's why they're saying it's high output, but it's not. It's like it takes a day to make that. So in terms of production rate per hour, it's pretty low. So for our community water systems, with the dissolved, we'll have these catalytic oxidation filtration systems. They're manganese oxide based. Direct oxidation and filtration, we'll use chlorine. For almost always we use chlorine. I'm going to mention something else later as well. But if we've got a chemical, it could be potassium permanganate. And with manganese, you often saw potassium permanganate, even on individual systems. Most of us don't really like them because potassium permanganate is a particularly nasty chemical to handle, turns everything purple. And ozone is like this a super, super strong oxidant. It's great. I sold on ozone equipment, and it is extremely difficult to deal with. It is just so aggressive. It wants to eat everything. Trying to keep it in its place is very challenging. You can smell ozone when you go outside and you get a whiff of, oh, wow, it's fresh air. That's the ozone you're smelling. And I used to say, I was quoting that movie, it's been too long since I quote it, but I'd go into the copy room and say, God, I love the smell of ozone in the morning, because that ozone is being generated by that copier when it's cranking out the papers. But ozone is not good to be hanging around in terms of occupational health and safety. So that's why chlorine, because we can get it in liquid form, is generally what we're going to use. The biological, we're mentioning the Suez because they have that Manganese treatment equipment process. There's not very many of them out there, and it's kind of unusual. And if it works for you, there's more and more people looking at it. It's more popular, say, in Europe. But if it works, it can work really well. And so engineers have been looking, and water treatment people have looked more at the biological. But for the most part, for small systems, you're probably, not that it can't be used, but there's not that many people using it here in BC. The particulate, we're going to have media filtration. With iron, I had customers that just had filters and it just filtered it right out. They didn't do anything else but filtering. And then if there's both in there, we might have some pre-filtration. And then again, we're talking green sand, but it's nowadays it's not very likely to actually have green sand. And I'm going to talk a little bit more about green sand. So it's this oxidation filtration is really what we're going to talk about. And so this was Dave's, and he had that it was robust with a wide pH. I put the question mark in there because wide is a relative term. We'd like that pH to be at 7.5, but you can be effective lower than that, and you don't want it to go too high for other reasons. We've got in here temperature range. So normally we're groundwater, and it depends on where that groundwater is coming from. So if you're right beside a creek and you're drawing it from the creek, one of the ways that we can tell it's coming from the creek is the temperature of the groundwater. If it mimics the temperature of the creek with a bit of a lag, then we think the water is coming from the creek. If the water temperature doesn't change as the creek temperature changes, then we don't think it's associated with the creek. We also use water levels in the well versus in the surface water. And if the surface water levels go up and down and the water well levels go up and down with a time lag in there, we'll go, we're thinking that they're connected. But generally speaking, the groundwater is going to the surface water as opposed to the other way around. But again, that's a generalization because you can be in a situation where that surface water is coming towards your well. But it's been underground, it's got these metals. There'll be some of them that are particulates and some of them that are still dissolved, and it's all dependent on all of that water chemistry that's going on. And I'm going to talk about other complications later on. So with or without a chemical pre-treatment, so generally with the chemical pre-treatment, the chlorine is preferred over the potassium permanganate and anything else. So here I'm mentioning the ozone and hydrogen peroxide. You're not going to see those. It'd be unusual. Ozone has been tried in small scales, but it is not, because of the difficulties of not necessarily just generating it, because there are companies that do make generators, but in getting the setup right and feeding it in. And then if you have other constituents, it can cause additional issues because it's such a strong oxidant. So the pre-treatment can even just be air. And back in the days when I was selling equipment, we were monkeying around with systems that were using air, and to a certain success. It's not as strong as chlorine, but it is the oldest oxidant that we've known, and where we get that term oxidation. Oxidation in general in chemistry is you don't need oxygen. It's talking about stripping off electrons, and on the flip side is that is a reduction where you're taking electrons away. But I'm going to specifically mention this newer concept of air injected oxidation. So at least one company has one of those filter valve heads that gets the air into it. I don't have a picture of one, but just know that it exists on the market. And if you can use just air, consider yourself lucky. So in the media that we use, in this filtration media, so again, we're going to oxidize and then we're going to filter. The filtering media is not just necessarily a filter, but it's also going to be a catalyst. And the original was this coated material called green sand. So you took sand and you put the manganese oxide on it as a coating. And it was cheaper, and technically it was a little bit easier to use than the solid form because it was lighter. Now there's green sand plus. Berm was popular 30 years ago, but it's got so many limitations, you don't see it very often anymore. But if you're going to use green sand now, it's pretty much always going to be green sand plus, I'd say. Then there's the solid stuff. So that's the manganese oxide mined out of the ground. It's just a little piece of sand that is the manganese oxide. Oh, I should have warned, my office is at home and I have a landline, which rings every once in a while. My apologies. So the solid, we originally just called that pyrolusite. That's a geological kind of term, right? Mm-hmm. Now we've got these different manufacturers with their versions of it. Phyllox is the one that you hear the most of. The other three, Mangox, Paralox, and Cadillac Light, are newer versions. And what they're trying to do is improve on that original form in various ways in its performance. And one of the things that is helpful is if you don't need as much water to backwash. So if you're taking your pump is feeding your treatment equipment, and then you go into backwash and it wants more water to backwash than when you're feeding it, well, that can be a problem. So some of these were developed to try and minimize that backwash, because when you're in the backwash mode, you have to lift that media bed. Usually it's, I think, about 30%. So that tank is not full. It's about 2/3 full, and then it backwashes and the media lifts. If you lift it too much, you start losing your media out the top, which can get expensive and reduces the amount of time between media changes. Most of these medias are fairly good in terms of these manganese oxide ones. They're longer lasting. Some other medias that you might see, this one is newer. Centaur has a catalytic carbon, so there could be specific water chemistries that would lead you to use that. And then on the ion exchange ones, there's some specialty ones that are available now to help deal with if you have higher organics. And Purolite is a large manufacturer, has been around a very long time, and I didn't even bother trying to list all the various resins that they had. So you can see that, in something that starts out simple, it starts getting complicated pretty quickly. But it's okay. We'll work our way through it. And this is basically the system you're normally going to see is one or two vessels, can be 3, 4, 5, just depends on the system. Then here we're showing that we're putting this oxidant in, and for us, it's almost always going to be that liquid bleach. And then we're going to have a chemical feed pump. It's going to be a peristaltic pump, a positive displacement pump, a diaphragm pump. And it's going to pump it in, and then you're going to curse it because the chlorine off gases a lot and wants to vapor lock. But the one thing is when you've got the chlorine, you can all of a sudden have a chlorine residual, and your EHO, your drinking water officer is going to love you for that. So this is a typical setup, one that we had been involved with recently. And there's the vessels, and there's control heads. And these vessels come in different diameters and heights, and they're tailored to how much flow you have coming in and out. And then you have, each of them has a control valve on the top. So what are some of these complications? Well, iron is a lot easier than manganese. Manganese creates smaller particles, and they're harder to filter. They take longer. So iron is easier, but often in BC we have iron and manganese. Sometimes it's just one or the other. It really depends on the rocks that this water has come through on the way to your well, and how long it's been underground, all those factors. And then in BC here, we often have arsenic. Arsenic is found many places in the province. Now, arsenic is something that we've been concerned with for a lot longer than the manganese. And one of the ways we deal with the arsenic is by using treatment process to reduce iron and manganese. So oftentimes we get the arsenic out, and then we get the manganese and the iron out as well. If there's not enough of the iron and the manganese in to allow us to take all of the arsenic out, then we might have a treatment process afterwards where we'll absorb the arsenic into a particular media that's designed for it, but now you've got a waste that you have to get rid of. And I should point out that all of these systems, we're backwashing them. You're sending highly concentrated manganese and iron out into the environment, so you have to have it's not a big thing, but it is a factor in consideration. So you don't want to waste, you want to have as little wastewater as is possible and somewhere to put it. Organics can be a problem. They come in very many forms, and it's like, what do you try to deal with first? Organics or iron manganese? And it'll affect the media that you're going to pick. Grant had given me a lot of tips about how they deal with this, and it was just going to be a little bit too much in a 1 hour thing. Ammonia is a big pain in the butt. Now, fortunately, we don't run across it often, but when you do, chances are we're putting some chlorine in, and all of a sudden ammonia is sucking up all of the chlorine, and you have to put a whole bunch of it in there to deal with the ammonia first. And then the reaction time that can happen can be very long. And if you don't deal with it properly, you'll be causing yourself all sorts of grief. We had a community that the chlorinator went in, and they really didn't like it because they had such a high chlorine level. The water came out, went past the homes, went past the school and the band office, and then up to the reservoir on the other side. So at the end of the day, we are going to try to change to a different source that doesn't have that problem. But in the meantime, we changed the timing to pump from the wells to the reservoir at night, so that it would get the highly chlorinated water passed into the reservoir, where it could sit and mix and then come back out, and the chlorine levels would be more acceptable to the community. They'll have had a chance to react. The reactions would occur. Wouldn't necessarily be good that they're happening up in the reservoir, but you can clean them. So these are the kind of complications you get. Hydrogen sulfide is one of these gases that's going to give you the rotten egg smell, which is also not uncommon here. And it's just something else that we have to deal with. And I'm not too sure. I was thinking that maybe the AIO ones might actually help with that, but I'm not too sure that they get rid of the off-gassing. It was something that we were trying to do in the 90s. And then hardness is a final thing. If you can have the trifecta of hardness, iron manganese, and one of the others, and then you're into multi-step processes. You could have a minimum of three different treatment processes involved to deal with all of them. And you can have, and with the hardness, often we use salt, and we do ion exchange, and now you can get into very high levels of salt consumption. Back in the day, our office was in the township of Langley. The hospital was nearby. We would bring in a truckload of salt periodically, and they would use about 3/4 of it. They used it on their hot water systems. The township had manganese in the water, and they needed to get it out on their hot water side, so they had a softener in there, and it worked for them, but they used a lot of salt. They came to us to see if they couldn't do something on their cold water side, but they didn't want to stay with softening because of the salt consumption. But their newer equipment back in the 90s was causing them to have to deal with it. And that's when I had the chance to work with Elmer Summerfield, who wrote the Iron Manganese Handbook, who's a very interesting guy and a pyrolucite nut. Oops. So we're getting close to the end here. First thing you do is go out and test and see what you have. With the manganese, you can try to find out what valence it is, and that can help. But not everybody knows how to do that, and we don't often do it. And you can ask for something called tannins and lignans to see if you got some organics, but otherwise we'll use total organic carbon to give you an idea. And if it's over 120, then what we need to do is protect our infants. So that we can do with bottled water or the RO under the sink to make sure they don't have it. And then the others, well, they can decide for themselves what they want to do. Unless it's over 300, then you're not going to necessarily worry about treatment for the entire community. My suggestion, though, is that aesthetic was set at 20 for a reason. Chances are, if you spend the money to put in the treatment and you can keep it going and it isn't, and the community can handle it, everybody's going to be much happier. So some type combination of filtration for the IWS, or I'm going to say most likely the softening and the RO are going to be the most common ones. Green sand in brackets again, or in quotation marks, oxidation filtration for community water systems is what you're going to do. It is very common. It's been around for a long time. And now we have these newer medias that have been really helping. They can handle wider ranges of pH, temperature, pressure. Actually, it's not the temperature and the pressure, but temperature and pressure do affect what happens. So it's in the ground under pressure. We take it out. It doesn't have the pressure. The temperature may go up. I was mentioning that before. The groundwater, the temperature is, generally speaking, it's about what your average mean temperature is above ground. That's what your groundwater temperature is going to be. And it's fairly consistent over the course of the year. But when you get it to surface, you're adding oxygen, and that complicates it. So I don't know that you're really going to have many of you on advisories, but if you did, oh, sorry, and the breakthrough is really something you have to watch here, because if you don't take care of your system, you could be spewing, you could be concentrating it in your filters and then spewing it out at a higher level than what it came in for a period of time. One other thing, and it's not mentioned here that I forgot to mention earlier, if you put in a system, treatment system, particularly if it's going to have oxidation in it and in chlorine and chlorine residual, If you can find somebody to at least flush your system, and if possible, swab it. So your chances are you got plastic distribution mains, and you put a foam swab into it, a series of them in an inlet point, usually by your reservoir or close to your pump house, and you push it through your distribution system to take all the stuff off the inside. If you're making upgrades, it's a good step. And then once you've installed your system, your drinking water officer is going to want to check your system afterwards and make sure that it's working properly before they'll lift an advisory. And the references here, Dave put these together. The last webinar is one done by Pentair on the air injected oxidation system. And they talk quite a bit about that, but there's a lot of stuff there about the chemistry and why the water is the way it is and the things that can complicate it. It's only just over half an hour long, so it's a pretty good review of what you're doing with manganese. And there is the website for the Online Help Center, which you probably already know because you're registered for this. And the last one is BCWWA's Small Water Network, which you can join, and then you can talk amongst yourselves in chat rooms and ask questions and try to help and support one another. And it's another resource. Of course, well, I hope you're all aware of your drinking water officer and talking to them and the different things that they expect to see. I didn't get into that, but it's probably, if you're going to start somewhere, they're not a bad place to start. Otherwise, you're going to be talking to a local vendor. Those are the people who are going to support you. Sometimes it's the people who are supplying your pumps, but not always. Sometimes they're going to be located close by, but if you're not close to Quesnel, Williams Lake, Kamloops, Prince George, you could have trouble finding somebody. There's fewer resources available in the East Kootenays. The Okanagan isn't too bad. The Lower Mainland, there's quite a few treatment companies, and a couple of them specializing in small water systems. So it can be a challenge trying to find somebody who's going to help you. But those will be the people that are likely going to be your go-tos, is your pump supplier and the treatment company that's closest to you. And I don't want to bash them. They'll often tell you it's quite simple, but I know from experience that the chemistry is complex, and sometimes you need to have patience and try different avenues. The pump part, that's the easy part. That's why I'm good with that. The treatment part, that's where it gets complicated. That's where I have to rely on people like Sanjana and Kimberly and Grant to help me out. But there are people out there who can help. And I think that's it. I've used up my time. So at this point, do we have any questions?
Yeah. Thank you very much, Ted. We will take questions from our attendees now. So there's a question from Collier. He asks, what areas in BC are common for arsenic?
Sunshine Coast and a lot of the interior, and the central interior as well. So in and around Prince George, up and down, we find it. So I don't know that there's any area in BC that really doesn't have it.
Okay. Our next question is from David. He asks, at my small water systems, we have 36 end user using groundwater from a well. The last test showed an aesthetic objective of 0.021 I don't know what the units are, micrograms or milligrams per liter, after treatment with only chlorine and a 5 micron filter. I took the water softener system offline about 6 years ago, but wondering if it makes any sense to reintroduce it. So he is able to achieve 0.021 aesthetic objective for manganese with this current system.
You're right. And so 0.021 is milligrams per liter, 20 is micrograms per liter. It's a difference of 1,000. So some people are, for the longest time, I would have used like 0.05. And Dave's presentation, he had 50. They're the same number. And because you're down at that level, if that's your treated water and you're far below the 0.12 to the 120 level, then you don't have any health issues that you're dealing with. Now it's aesthetic. So then the question would be is, what's it like in your distribution system? And are people complaining about staining? And if they are not, then you're saving on sodium. And if they are, you can try reactivating your softening system, but it may be that you'd need to change the softening media. We've had situations where when there's been problems with the media, that the vendor just wants you to buy entirely brand new vessels and not try to change the inside. And I can tell you that changing the inside can be a real pain, and sometimes nearly impossible, but you know, those are the kind of things you're dealing with. But you can always try sparking it up and see if it works.
Okay. Thank you, Ted. Next question, again from Dave. How frequently do you recommend testing to confirm that the treatment system is working well?
Okay, that's a great question. I should have mentioned it somewhere along in there. So first off, there are manganese test kits that are available, and we use them quite a bit. Hawk is the biggest company, but there are others, and they use primarily what's called DPD, which is a particular method, a chemical method that you would use. And my colleague Danny forbade our communities from using it because it has cyanide in the reagent. So you add this reagent and then you get a color change and you see what the level of manganese is. So it's not, you know, as a community water supplier, you might invest in one of these Hawk kits and have the ability to do it. But if you had that, the Occupational Health and Safety, the MS, the Material Safety Data Sheet, tells you that you have to use it with a fume hood. So one of those things you had in high school, you know, it sucked all the chemicals off when you're doing certain reactions. And we had operators complaining that when they were using these test kits that they got headaches. So, so precludes doing anything on site. So that means you're shipping it to a lab and you can pay $25. So chances are you've already had a test done on your raw water. If you haven't, you should take it and send it off to the lab to see what it is, to make sure that you have water that's under 120, for sure under 300. But you want to have it 120 because if there's any children, any infants on your system, you want them to be protected. But the first thing you do is just make sure the mom's using bottled water for them. And then the second thing is that individuals can install those under sink ROs. So you send your test off and check it. Now with groundwater, it tends to be relatively stable over time, but it can be influenced, like I said, if you've got that creek source that changes your water quality, that quality can vary. But generally it tends to be pretty stable. So you do the test, and it'll be done as part of a fairly low cost. All the labs offer a small suite of parameters: the hardness, the TDS, the iron, the manganese, often the arsenic as well. And that test is not particularly expensive. So you can have that done. And then it's a question of how often do you retest? Well, with the bacteriological, your drinking water officer will say, if you're a small system, you should be testing once a week. But for manganese, you probably wouldn't do that. You might start off, like you've got a hydrogeologist come in, they probably recommend starting off with a monthly program. they'll be looking at that source water protection zone. I don't know if any of you have heard of that, where you're looking at where does your water come from. And the reason you do that is because the most important thing is bugs, and you need to know if you are influenced by septic fields or they're too close, then you have viruses. That's going to make people sick. I never got into that, but it's a big part of understanding what the safety of your water is. And bugs are the #1 thing that kill people, and they can kill people relatively quickly, and outbreaks are associated with them. They're generally related to water quality changes. So I remember a few years talking in Penticton to a small water systems audience, and I was saying, what was happening right now? Well, there was a lot of flooding. And I'm like, that's when you want to check your water, is when it's flooding. When is it affecting? Keep an eye on your water quality. When the floods are happening outside, is the quality of your well water changing? And if it does, then you put up red flags. So you look at where your source water is coming from, and then you can decide, well, it's pretty stable. You might test monthly and then go back to once every 3 months, then every 6 months. You might do it once a year. Sometimes it can even be longer, but it's all dependent on your particular situation, and everybody's unique. But with manganese testing, it's not likely you're going to be doing it a lot. Now, the difference is once you put your treatment equipment in, then that drinking water officer is going to want to know that it's working if it's for a health limit. Okay, so if it's for a health limit and you don't have bottled water under sink RO for infants, then now you as the purveyor are having to make sure it's always meeting that. Again, it's not like a light switch. It's an exposure, but for infants, that is not like a lot of the things like arsenic. That's a 70-year lifetime exposure, but for infants, it is not. They couldn't have been an infant for 70 years, so it's a short-term exposure for them. And you can get what they call breakthrough with a lot of these treatment systems. So once you have treatment in it, chances are it'll be your drinking water officer who's going to stipulate it. But if your water is causing staining when it's above 20 or 50, if it's going over 120, you already know it's over 120. So those are the kind of the good things about having to deal with manganese at this maximum acceptable concentration. But if your water if it was all dissolved form before and you're not seeing it, well, you're going to have to test and be watching for it. And I'm guessing they'll probably be looking at perhaps monthly tests, $25 a month. It's easier to do. At least it's well, I shouldn't say this. I'm not a testing person, so. But I think it'd probably be less of a problem than trying to get your back teas to the lab in the short amount of time to have them be valid.
We have a question from Robert. Have you had any experience with sequestering agents to keep the manganese in solution when the groundwater manganese source level is below the maximum allowable concentration? But there are aesthetic concerns, i.e. precipitates in the distribution system and staining.
Yeah, that's a good point. We actually probably should have included sequestering. It is used and can work. The city of Prince George used it for a long time. I think that in this particular case, though, in terms of that's more of something you're doing to keep things insoluble and from staining. But this with manganese, that's not in this particular what you're trying to go after here. There's no difference between what the manganese is coming in at in terms of the MAC. So the fact that it's not causing you problems doesn't get you off the hook. So it could be the reason why Dave never included it in the first place. If you're simply doing it for an aesthetic concern, then it is something that can be considered. But it's also something that it's a chemical that you're going to put in to keep the manganese in the yarn from causing problems. And the reason it's done is because it can be cheaper to just inject this chemical than to try and put in a filtration system. In the long run, I think generally consumers are happier, customers are happier when we get the material out of the water. But that's not every case. That's generally more when it's causing the staining issues, when it's, hopefully that answers the question.
Next question is from Marcel. Is there a geographical trend with respect to where one would see more dissolved manganese versus particulate manganese in groundwater?
Not that I'm aware of in terms of mapping done in British Columbia. There is lots of aquifer mapping that's going on, but there, to the best of my knowledge, there hasn't been a lot of tracking arsenic, iron, manganese hardness to these various aquifers and how they're causing problems. And some of them are fairly small in extent, so they don't affect very many people. So in Medley, they have an aquifer that has arsenic, but it doesn't affect very many people. So I don't know that there's a lot of impetus to try and track these things. I think with modern data, you probably could start to do that, trying to pull water quality, but the various organizations don't necessarily talk to one another. So trying to get the information. So if you went to the health authorities and said, you know, we know you have this information, can you dump it and give it to us? It's like they don't have people there to do it. They don't get any funding to do that. So trying to do this from a research perspective is a challenge. Often thought if I became an ultra billionaire, I'd be doing these kind of things just for the fun of it and to see if it couldn't have a good outcome. But it's a good idea though.
Is there a general level of manganese in groundwater that water softeners can treat below the maximum allowable concentration, i.e. will water softeners typically drop manganese? I lost my question.
Yeah, no, and there is a
from three. Sorry, Ted. Will
yep.
The water softening typically drop manganese from 300 to less than 120 micrograms per liter? And this question is asked by Shane.
Right. Okay. I can't answer that one off the top of my head. I'm not smart enough to remember all of the numbers, but it's a good question, Shane. And so there's guidances about the levels that you can use ion exchange to tackle iron and manganese. But that's something that you talk to with the person who's going to supply you the equipment, and you'd ask them. And the person that's, so for instance, Purolite will have data sheets that tell you what they think their particular ion exchange resin can do. But you get into all the caveats about, well, what else is in the water? So there's never any simple answer with this water chemistry. I'm thinking, I don't know that softening would be the go-to with those levels of manganese.
Yeah. Okay, next question. For small water systems, do indigenous water systems require using a dedicated water reservoir with potable water for backwashing and rinsing media, or just using raw water? And the question is from Li Yang.
I love that question. So the requirement of using treated water to backwash is not a health question, but it's more a technical question. And the reason to use treated water is twofold. One, it doesn't have the stuff that you're trying to take out of the water in it. You've already taken it out. So when you're backwashing and rinsing, you're not adding, you're getting it cleaner. And secondly, I mentioned before that sometimes your backwash rates can be fairly high. And so when you're using treated water, if you have enough of it stored, and that's a question, so it depends on your system. She mentioned a reservoir. If you have a reservoir, you have enough. If you just have pressure tanks, not so much. That's likely not going to be enough water on the treated supply side to use it. Might be, but probably not. So that's the benefit of using the treated water. Many systems, many small water systems using groundwater do not have reservoirs. They pump directly into the system, and they almost always have pressure tanks. Now you see more often a frequency drive with pressure controls to ramp pumps up and down. The pressure tanks were there to even things out and make sure the pump came on and ran for a minute or two before it would turn off in the middle of the night when the water system is leaking a little bit of water but not using much. So those are the pressure demand systems, and they're not uncommon in small systems. These are systems that are probably in the 10 to 50 connection range, close to the 10. By the time you're getting to 50, you're starting to look more like a real system. You could very well have a reservoir. Historically, those reservoirs floated on the system, so they were on the far end. So that was like the community I was saying earlier. The wells pumped right into the distribution system in the middle of the community, and the reservoir was at the far end of the community, past all of the homes, past all of the buildings. After I came to the department, I started pushing for what we call a dedicated water main. So we go from the treatment point, from the wells, wherever we're doing the treatment, and then we have a water line that goes up to the reservoir. And there's a couple of benefits to this. Well, there's more than two. One, the water that you have in that tank, you want it to be fully mixed. And you can't tell the difference between water in the corner, the top, the side, the middle. The temperature is the same, the pH is the same, the chlorine residual levels, all the same, all of the water looks the same. And that's the best way to store your water. And if you have a dedicated main coming in, it's easier to achieve that. It's not impossible to do it the other ways, but it's not as easy as when you have a dedicated main. Second thing is, so if you're using a chlorine residual, so the department since 2006 has asked for First Nations to have a chlorine residual. And so many small communities are not, they haven't had chlorine and they're not necessarily looking to have a residual disinfection. And so they might say that they're not happy with chlorine and they think it caused taste and issue orders, but often that's related to other things. But if you have this dedicated main, you can get what we call a contact time. So the number one concern you have with your water well are viruses. Viruses are tiny and they can travel through the ground. Giardia and crypto, those are big. The ground filters it out quite quickly. So you have to be in a really sandy, gravelly aquifer, really close to a surface water to get a Giardia and crypto in. If you do, that's a GARP well, groundwater at risk of containing a pathogen. The bacteria we don't really look at, because if you have bacteria, chances are you have viruses, and the viruses are the thing that we're looking at trying to get rid of. And if we can get rid of virus, we can get rid of a bacteria. If you have the Giardia and crypto, you can get the bacteria, and the one we're looking for is, of course, E. coli. So all of this is, what do you have in your source capture zone? Do you have septics or a sewer force main in your capture zone? If so, you should be disinfecting, even if it's a UV. But if you have iron and manganese, your UV is not going to last very long. So now you're going to have treatment to have your UV. So there's a lot of small systems that are at risk and they are not having adequate disinfection. And they're only lucky because guess what? If it's a virus, it had to come from you and I, and we already live on the system. So we probably would have infected ourselves with the virus just through our normal everyday lives. But if somebody new comes to the community, they're at risk, and they're at risk of getting something or bringing something. So at any rate, totally in on dedicated mains and using treated water for backwash. Both good ideas.
I think the next one might be just a comment to a question that was already asked. But I think, Robert, it makes sense that you would see increase in turbidity. So he's saying our well has a manganese level of 0.06 milligrams per liter with turbidity of 0.3 NTUs. However, once the water enters the concrete storage reservoir, we're assuming it is being oxidized when in contact with air, and then the turbidity increases to more than 1 NTUs. So that does make sense, especially if you're chlorinating as well too. So
yes, yeah, and we have had people that have designed systems in the past, particularly with iron, and when they put the water into the reservoir, they splashed it onto a plate or did something. And I was talking to my colleague about this, that there are treatment systems, we didn't mention them here, but they would just cascade the water down over some type of system. They were these kind of like wiffle ball things. They were very open and trying to and get oxygen into air into the water, which is mostly nitrogen, but there's enough oxygen in there to help to try and increase the dissolved oxygen, maximize it, get those reactions to happen. And we had a community that was tried that with manganese, and the water treatment engineer whom I respect the most says, Ted, that probably wouldn't work because the manganese takes too long to react. And I laughed. I said, yeah, no wonder why it's not working. So, and the other thing is too, is if we're doing that, what we're doing is we're getting material coming out. And I remember a consultant proposed that, and it was a very large reservoir. And I was concerned about the amount of manganese that had come out. He did the calculations, and it seemed to be not very much. And it's like, wow, I would have thought it would have been more stuff on the floor of the reservoir. So then it's a question of what's the outlet for your reservoir? Is it properly installed? It's not supposed to be on the floor. It's supposed to be up above the floor so that stuff on the bottom doesn't go out. And then there's a drain line that is flush with the floor. But to go into your reservoir, you have to have a confined space entry program that is written by an occupational health and safety specialist, and your community has to have a confined space program. And many times people go in there without that, and you're putting yourself at risk if somebody is, something happens to a person inside of a confined space. And I've been on probably hundreds of confined spaces. The last one when I started with the department, and then one day I realized that's probably really, really stupid to do that. And that was the last time. So trying to have it come out in your reservoirs, it's an option, but is it the easiest one? I don't know.
Yeah. Mike, I don't know if we can make a recommendation about a provincial lab. So Mike is asking, is there a name of a provincial lab for inexpensive testing? I don't know if Ted can answer that. We're not allowed to make a recommendation, but if other small water systems are there, maybe they can put it in the chat as to who they might recommend as per a lab, inexpensive lab. Ted, do you want to add anything to that?
Yeah, no, I don't think you're going to find a great difference, but there's no harm in calling various labs and getting them to give you a quote. And so when Danny had checked in, it was about $25 to do the manganese, but that was some years ago. Maybe it's gone up now with supply chain issues, etc. But they're all, you can find all of them doing your Google search, and you can contact them on their websites. They probably have lists of tests and what they do and how much they are. I haven't gone and looked, I haven't tried. For Indigenous communities, First Nations Health Authority will do a test of a large number of parameters once every 5 years. When we do our improvements, we do a very exhaustive test at least once before we do the design for everything that has a MAC, a maximum acceptable concentration. But that's like an expensive test, so we don't do it very often. For the manganese, I would check around, find out who's the closest one that you can get to, because you've got to get them there as well. And that small water network is a place where you can exchange that kind of information as well. I'm not too sure if there is something within the online small systems that does that.
Next question is from Brian. Ted, can you provide any comments, pros and cons about the use of potassium chloride rather than sodium chloride for water softening? Also, do you have a preferred particular softener type, like a sodium chloride or potassium chloride in the treatment process for manganese?
Yeah. We did try to investigate potassium chloride, and we didn't have much success. It's about 2 or 3 years ago. So trying to get it, I think, would be the challenge. So you're going to have to, that's again where you got to find a local vendor, or unless you're really savvy. We did have a community that was going to have limestone chip to themselves. They found a quarry and they were going to have it stuck on a rail car and shipped over to them, which I thought was pretty impressive. But normally you're just going to try to find a local supplier. So most, even smaller communities, if there's like a Home Hardware, Home Depot, you know, one of those, the Rona, oh no, they're not Rona, but Lowe's, whatever, they often have salt. They sell softeners and they have the salt. The rub is that you're not going to find anybody who's a real expert. Then you go to the water treatment companies. And I think the biggest thing is you're just not going to find people who have the potassium chloride.
Okay. Another question from Mike. We have a community water system. We have that dark brown stain occurring randomly and at random times. Any thoughts?
Yes. It's because your water quality is affected by so many various parameters. So we didn't talk a lot about temperature and pressure, but those are two factors that people often don't think of that affect it. I'm not saying that was your situation, but it's also the residence time, the amount of time that it has to react in your system. So if you didn't have a reservoir and it's just going straight into your system, then you can have some high variability. If it goes to a reservoir, that kind of buffers things out. And also, then that's where you're starting to look at your raw water quality and your source water. If you have a water well, you should be thinking source water protection plan. You should be thinking about where your water is coming from. And I'm not saying that's an easy thing to do, because if you hire a hydrogeologist, that's thousands of dollars for them to look at it. And at any rate, it's likely going to be variability in the incoming raw water quality, but it also can be related to distribution time issues. Like some communities, you can have water sitting in lines for a long period of time before they're used. So that depends on how the distribution system is set up. And I can tell you this, when you start getting to those kind of problems, it can be very tricky. Oftentimes, I'm on calls with people from FNHA, the consulting firms, ourselves. We have our circuit riders who are advanced operators doing training, and we'll struggle trying to figure out why problems are occurring. And it can be very discouraging, but it is the reality of being a water supplier.
Okay, great. Thank you so much, Ted. That was an excellent presentation, and we had some great questions from our attendees. So thank you everyone for attending. If you have any more questions, please put them in our, please email them to the Online Help Center, and we'll make sure that those questions are addressed after we conclude today. I do have a question about how you get your CEUs for this presentation. So what will happen is that our system automatically generates a CEU certificate for you, and then it's up to you to submit that to EOCP to obtain your CEUs. Our next webinar is scheduled for Tuesday, January 24, 2023, same time, and it will be Ask the Drinking Water Officer, where we will have Robert Birtles from Interior Health, the Environmental Health Officer, answering any questions that you may have about small water system regulations and legislations, and so on. Okay, and then make sure check the website again for the schedule for 2023 webinar series and the free courses. They're all posted on the website, and make sure that you register. Again, thank you so much for attending, and thank you to Ted to giving us his very important time to help with small water systems and all the issues and concerns they have in making sure that they're delivering safe drinking water to their communities. Thank you very much.
Bye, everybody.
Okay.